folks. For those of you who have sent me emails and are waiting for me to reply, I've been kind of sick the last few days, so please be patient a few days more. Today I'm going to talk about disjoint sets, and disjoint sets is a data structure, singular even though it has an S at the end. It's a single data structure that's designed to represent a collection of disjoint sets. And what does disjoint mean? Disjoint means that no item is in more than one set. So you have a bunch of items, and each of them is in exactly one set. Now, the collection of disjoint sets together is called a partition. Partition is a mathematical term. A few of you might have heard of it. It's basically any way of taking a set of items and partitioning them into several sets of items so that each item appears in exactly one set. So we assume that we have a universe of items. And the universe is just all of the items that can be a member of a set. And again, each item is in exactly one set. So one example where this might be useful is if you have items, a universe of items, each of which is either a corporation that still exists today or a corporation that existed once but then was acquired by another corporation. And so for instance, you might have three different items named Microsoft, Forethought, and Web TV, and each of those items now belongs to the Microsoft set. Now, our data structure is going to more or less limit itself to two questions, or at least two kinds of queries that we can do very quickly. So the main two operations that a disjoint set data structure supports is the union operation, which merges two sets into one. And then there's a find operation. The find operation allows you to ask a query like, what corporation does Web TV belong to today? Or in other words, it takes an item and tells us what set it's in. Now, we're not going to support operations that take a set and break it up into two separate sets, or at least we're not going to support them very quickly. These are the two operations that are going to run fast. And data structures that support these operations are often called union-find data structures. Disjoint sets is another name for the same thing. So what are things you would want to use this for? Well, actually, we've already seen one application of this, which is Kruskal's algorithm. So you might recall that in Kruskal's algorithm, we look at an edge that connects two vertices, and we're asking, should we or should we not add that edge to the graph? And the answer is, if those two vertices are connected to each other by a path in the graph, then no, we should not connect them because that would create a loop. If they are not connected by a path in the graph, then we should add the new edge, and that will connect them together. So when I gave the lecture on Kruskal's algorithm, the only way we had to do that test was to do a depth-first search from one node outward and see if we could reach the other node or not. That's the slow way to do it. The fast way to do it is whenever we create a new edge, that's going to join two parts of the graph together into a single set. So I'm going to have a bunch of disjoint sets where initially each node is in a separate set, but whenever I add a new edge to the graph, that melds two sets together into one. And when I'm done, the entire spanning tree will meld the whole graph together into one set. But along the way, I need to be able to ask queries about, are these two nodes in the same set yet, or are they still in different sets? If they're still in different sets, I can add this new edge. If they're in the same set, then I can't. So we're going to see how to make that go fast. Any questions so far? By the way, Project 3 is available, and you're also going to need, well, you're going to implement Kruskal's algorithm, so you're going to need to understand this. And you're also going to use a union find algorithm in homework 9 to create a maze. So here's an example of some sets we could work with, or a universe of items. Here's some corporations. Piedmont Air. Empire Air. US Air. Pacific Southwest. Web TV. And Microsoft. So at this point, if I do the query find Empire Air, then that gives the result Empire Air. So Empire Air, and like every other item, starts off in a set named after itself. Now I'm going to do some union operations. So at one point, some years ago now, Piedmont Air took over Empire Air, and US Air took over Pacific Southwest. And so where there was just 6 separate sets, now there were only 3. And after those union operations are performed, you can do this same find operation all over again after the first 3 unions. And you'll get a different answer. Now if I do find Empire Air, the answer is Piedmont Air. And later on, US Air took over Piedmont Air as well. So you can do a union operation that takes the union of this set with this set. So we do one more union operation. And now the answer is US Air. The results of a find operation can change after any union operation, depending on what got unions together. Any questions on that? All right. So there are 2 different data structures you could think of for the union find operation, or that we'll discuss. I'll only briefly discuss one, just because it's the obvious one that you would probably think of first. So the idea of list-based disjoint sets is, let's do the obvious thing where each set is going to have a list of all the items in the set. And each item will just know what set that it's in. Seems obvious enough. One of the nice things about this is how the find operation works is really, really simple. Each item knows what set it's in, so you just return it. And that takes order one time. The disadvantage of this algorithm is the union operation. So suppose you have two sets, and each set has n items in it, and you want to merge them together in one big set with two n items. Well, you have two lists. You can just concatenate those lists together, and that gives you your new set list. So that's easy. You can do that very fast, concatenate queues. The hard part is that each item references the set that contains it. So I need to go through one of the two lists and relabel every single item in that list so it knows what its new set is. And so the union operation is slow. And we can do much better. If you want to look at this particular data structure in these algorithms anymore, well, there's two ways you can do it. One is Goodrich and Tomasia cover this in section 10.6.2. And I've asked your TAs to cover this in somewhat more detail in discussion section, so that I can go on and spend most of my time on the faster algorithm. But before I do that, any questions about this? All right. The faster algorithm is a somewhat less obvious data structure. These are tree-based disjoint sets. Now with the list-based disjoint sets, the algorithm that does the union find on them is sometimes called the quick find algorithm because find is fast, but union is slow. With the quick union algorithm, union will be the faster of the two operations. In fact, union will run in constant time. Find will be slower, but not much slower. One problem is it's actually pretty complicated to say exactly how slow it is. But let's look at the data structure. It supports constant time union operations and somewhat slower find operations. Keeping in mind that quick union will be faster overall, for any sequence of union and find operations, then the quick find algorithm that runs on these list-based disjoint sets. So first of all, in order that we can support really fast union operations, each set is maintained as a tree. Not a binary tree, but a general tree. So the data structure for the whole disjoint sets structure is a forest. So what's a forest? It's a collection of trees, you might recall. And each item is initially the root of its own tree. Because each item is initially in a separate set. So one of the things that makes this algorithm interesting is, at least for the basic version, if you just want to do union and find operations, this tree structure is even simpler than the ones you've studied before, because all you need are parent pointers. You don't need any child or sibling references to make this work. Every node knows only its parent. And if all you need is union and find, that's sufficient. And finally, the true identity of each set is recorded at the root. Now, union is a pretty simple operation with this data structure. A union operation is done like this. You make the root of one set become the child of the root of the other set. That glues the two sets together. So for instance, once upon a time, Piedmont Air was a root node all by itself, and Empire Air was a separate root node all by itself. But then we glued them together, and so Empire Air gained a parent, namely Piedmont Air. The same thing happened with US Air and the Pacific Southwest. And where things get interesting is when you have sets each having more than one node that you union together. So now I've got these two different sets. There's the Piedmont Air set and the US Air set. And I can take the union of those and merge them all into one big tree, now called US Air. So union is simple. Any questions? Find is pretty simple too. So to do a find operation, you start at the node that you want to query. Like, for instance, maybe I want to know what set Empire Air is in. Well, it's just a matter of following parent pointers. So I follow Empire Air's parent pointer, and that puts me at Piedmont Air. I follow Piedmont Air's parent pointer, and gets me to US Air. I follow US Air's parent pointer, and it doesn't have one. Well, it's null. So US Air is the identity of the set that Piedmont Air belongs to, or that Empire Air belongs to. And that's how you do a find operation. Just block the parent pointers. Now, this is obviously the more expensive operation because it might go more than one step up. So the cost is proportional to the item's depth in the tree. Yes? Mm-hmm. Uh-huh. Well, two reasons. First of all, the first time you do it, it'll be expensive, but we're going to do something called path compression that'll make it cheaper every subsequent time you do it. And not only will path compression make this find operation cheaper, it'll make other find operations cheaper as well. So when we look at the average performance of the algorithm over time, that'll be trickier to figure out. And second of all, analyzing something in terms of the depth of the tree isn't really satisfying. You really want a bound in terms of the number of find and union operations that you do. And so, well, I can say that the depth is not greater than the total number of union operations that we've done. So that, there's a bound. Cost is proportional to the total number of union operations I've done in the past. But we can actually do a lot better than that. Other questions? I'll talk about analysis again at the end of the class. Now, again, since the cost is proportional to the item's depth, we want to keep that depth from getting too big. We want to keep any item's depth from getting too big. So there are two extra tricks that we add to the algorithm that will help a lot in keeping items at a very shallow depth and at keeping find operations fast. So the first one is we want to keep items from getting too deep in the first place. And so here's how we do it. Well, at each root, we're going to record the size of the tree. By which I mean the total number of nodes in the tree. And then whenever we do union operation, we're going to make the smaller tree be the child of the larger tree's root. And this strategy is called union by size. So here's how union by size works. Suppose I have a tree like that, another tree like this. Am I going to make this one be the child of this? No, that would be stupid. Of course, I do it the other way around. And if I have another tree like this, then, again, make the smaller one a child of the bigger one. And this tends to keep trees from being able to grow very fast. So, for instance, let me point out that the only way you can get a tree of height 2 is to take two trees that each have at least 2 items and then take the union of them. So that gives you a tree where you actually have to take 2 steps to get from one of the nodes. The only way to get a tree of height 3 is to take 2 of these trees of height 2, well, or of size 4 or higher is what I really should say. 2 trees of size 4 or higher, and union them together. There's no way with union by size that you can get a tree that has height 3 and fewer than 8 nodes. If you want a tree of height 4, well, you have to take 2 trees that each have at least 8 nodes and union them together. And that gives you a tree of height 4 sometimes. So maybe you can see where this is going. Every time I increase the height of the tree by 1, I've doubled the number of nodes I need at the minimum to ever obtain a tree of that height. So these trees don't grow bigger than logarithmically in height with the number of union operations that have been done. Question about that? Yeah. A new tree, a child of a root node. Uh-huh. Uh-huh. I'm not sure what you're saying. In what I do that? Uh-huh. Well, I mean, it's not always a new tree. So I could take any two arbitrary trees, and I don't know which one is new and which one is old, and they both might be quite big trees. And I need to decide one of them has to become the child of the other. How do I decide that? Does that make sense? I mean, if it's a new tree, sure, always make it the child. But for old trees in general, I don't know. Question? Well, if you do that, so you're saying take all of these pointers and make them point to the other tree's root? Okay. So you could do that. The thing is, you would actually have to walk through all of the nodes in the other tree, and that would actually increase the time compared to what our algorithm is going to take. You're right, but I've got a second trick, and that's going to help find even better. Yeah. What if you were to half? Uh-huh. Only walk halfway up the tree? Well, then you're reducing the running time of your algorithm by a factor of 2, but I want an asymptotic improvement. So I say I can do even better. That's my answer. So before I go on to the second trick, the other trick that makes this super fast, I want to start establishing a concrete implementation so that we can use that as something that gives us a clear understanding of what's going on here. And once I've got the foundations of an implementation laid out, then we can go on to the second trick to speed things up. Now, you could, of course, implement quick union with tree nodes and create tree node objects. But if you want the absolute fastest implementation in terms of not only the asymptotic bounds, but also making the constant factor hidden by the big O notation as small as possible, then there's a really slick implementation that uses an array that I'm very fond of, and so I'm going to teach it to you. Here we're going to make the simplification that we have items that are numbered from 0. So the items are integers from 0 to n minus 1. You can always add new items dynamically if you want by resizing this array. So the array's job, it's going to have two jobs. One of its jobs is it records the parent of each item. But I'm also going to use a kludgy trick where if an item has no parent, then instead I'm going to use the same array to record the size of its tree. In the same array. So this is a kludge, and the way it works is that to distinguish between a parent pointer and a tree size, I'm going to make the tree sizes negative. So if I have a tree whose size is 3 nodes, I'm going to store a -3 in the array for the root of that tree. So now I'll draw these so you can see them. So when we first start out, every node is in a distinct set. So here are the indices for 10 different items. Initially, every item is in its own set, and the size of each of those sets is 1. So I'm going to write a -1 into every box. So that's what the disjoint set data structure starts out looking like before I do any union operations. But then, well, let's do some union operations. Suppose I wind up with trees that look like this. So eventually, after doing some union operations, I have my items in 3 different sets. And here's how that's going to look. All right, let's start with item 0. 0's parent is 1, so I enter a 1 in 0's box. 1's parent doesn't have 1, so 1 is a root node, and I use a negative number to symbolize that. And the negative number is a -4 to remind me that there are 4 items in 1's tree. 2 does not have a parent. It's its own tree of size -1. 3's parent is 8. 4's parent is 5, and 5's parent is 8. 6's parent is 1. 7's parent is 3. 8 has no parent. 8 is the root of a tree of size 5. And 9's parent is 1. So that's what the array-based disjoint set data structure looks like for these particular disjoint sets after some sequence of union operations. I'm going to give you code for the union operation with union by size. Wrong order. So the way this very simple union operation works is we take the roots of two different trees, and we're going to union them into one tree, and we're going to use union by size. So the first thing we do is we compare the sizes of the two trees and see which one is bigger. Now remember, I'm storing the tree sizes as negative numbers. So if this is true, then that means that root 2 has a bigger tree than root 1. And if root 2 has the bigger tree, then root 2 stays the root. And so we update the size of root 2's tree. So all of the items in root 1's tree now get added into root 2's tree. And we make root 2 be the new parent of root 1. Otherwise, in the reverse case, root 1 has the bigger tree, or at least the equally sized tree. So we make root 1 stay the root node and root 2 be the child. So we update the size of root 1's tree. That's it. Really simple. Let me say about this that this is not a very well encapsulated union operation, though. And the reason why is that a good union operation would hide the fact that certain nodes are roots of the tree. Because really, a disjoint set data structure, all the external caller is really supposed to know is that this is a set. They're not supposed to know that one of those items is special, because that's an implementation detail. And so really you'd like to hide that implementation detail. So what you really want to do is you really want to start this by doing a find on each of these two nodes, finding the roots of the two trees, and then doing the union. But to keep it short for class, I've just given you the not very well encapsulated version. Any questions about that? Yes? The problem, okay, so that's a good question. Wouldn't it be better to record the depth of the tree? The problem is that the next optimization I'm going to tell you about fudges up the depth of the tree, and you're not going to be able to figure out what the depth of the tree is without doing a really slow search through the entire tree. We don't want to do that. It turns out that union by size and union by height, as it's called, both give the same asymptotic bounds, but union by height is something you can't actually do. Yeah. I don't think so, no. Actually, I think that in practice, the way people are really going to use this is they're going to do a union operation on, say, remember the Kruskal algorithm? What you need to do when you are in this position where you want to know if these two vertices are connected to each other, you pretty much have to do a find on this one to find out which set it's in, a find on this one to find out which set it's in, and then if you decide to add this edge, which you can only do if they're in two different sets, then you do a union operation. So, well, and if you've already done the find operation, then the next optimization I'm going to tell you about will have compressed these paths, so the doing find again will be super fast. So, in fact, why don't I tell you about path compression now? All right, so here's the trick. suppose I have a tree like that, and I do a find operation on node 7. So to do that operation, I need to start at 7 and watch the parent and watch the parent and watch the parent. And when I'm done, I find out what the identity of the parent node is. It's 0. Well, since it takes virtually no extra effort, why not adjust these pointers so that every node I just went through points at the root? So this is a lot like the idea that some of you had for relabeling the vertices in the tree so that they know the root node, but we do it in a lazy way, which is we don't do it until there's a reason. Like, if no one ever does a find operation on the 7, then why waste time fixing its pointer? But if someone does do a find operation on the 7, then the first time they do that, we're going to fix up its pointer so now it points to the root of the tree. And if we ever do the find 7 operation a second time, well, now the 7 is right up there near the top, and the second time it'll be super fast. So, I guess the part I want you to write down is that part. So doing this is called path compression. Any questions about that? Here's the code that does it. So the first thing we're going to do is we're going to test if we are already at the root. And we know that we're at the root because our array value is less than 0. And if that's the case, then you return yourself, because I am the root of the tree. The other case is if you're not the root of the tree, then you have to walk up and follow your parent pointer. So we're going to do that in 2 steps. First step is the path compression step. There's a lot packed in this one line, so let's look at this carefully. What this line of code does is, first of all, it looks up the identity of your parent. Second of all, now that you know who your parent is, you call find recursively, and that'll find your grandparent, your great-grandparent, so on, whatever. Keep on searching up to the root of the tree. And when it's done, it will return the root of the tree. So now when the find operation recursively returns, now you know the root of the tree, so you replace the old parent pointer with a new parent pointer that goes all the way up to the root. So all that in one line of code, and then you just return that value, because that's the identity of the set that you're in. So all in all, you can see the code's very short, very slick, runs super fast, does a lot more than it looks like for such a short piece of code. Any questions about this? So the running time of quick union, well, the union operation is very easy to analyze. It takes what's called theta 1 time. Yep. And it's pretty obvious if you look at the union code, though I just erased it, but the union code has no loops, has no recursion. It just does a few things once, and so it's obviously take theta 1 time. The find operation, well, so it could take theta log u worst case time for one such operation, where u is the number of union operations. That took place prior to the find. And the reason for that log u again is my observation that the only way to increase the height of a tree by 1 is to at least double its size from the minimum possible size. And so that's what union by size buys you, is that it's only log u in the worst case. But you can analyze not just the worst case, but the average case over a sequence of operations, and that turns out to be even better. So the average running time for any sequence of union and find operations is close to constant per operation. It's so close to constant, in fact, that it's almost, you can almost pretend that it is constant for any real-world application, but for the exam you should know that it actually runs slightly slower than constant. And here's the facts. A sequence of ffind and union operations takes something called theta of u plus f alpha of f plus u comma u time. What is that alpha? That alpha is something called the inverse Ackermann function. And it's an extremely slow-growing function. In fact, this function grows so slowly that it's never larger than 4 for any values of f and u that you could ever possibly use on an actual computer. So you could almost think of this as running in u plus f time, except technically, in a rigorous mathematical sense, it's not linear time. It's slightly slower than linear time. Unfortunately, defining the inverse Ackermann function would be 15 minutes of lecturing itself, and probably not all that enlightening. So I'm not going to do that. But are there any questions on this? Yeah. Much slower than log of n. Much, much slower. It's slower than log of n. It's slower than log of n, you know? All right. See you Friday.